In this tutorial, I will give a demonstration of using R for Anova. There's a lot more than can be done here, but this is the introduction. The first thing I'm going to do is attach a data set that has values. In this case, it's going to be weights of chickens versus 4 different kinds of diets. So I attach chick weights, and it's a good thing to look at what you attach, check it out. So actually there was more than that. There was quite a few things that they fed these chickens that were different. So here you got the weight of the chickens versus horse beans and linseed and soybeans and I don't know, meal. So I'm going to take this data and I'm going to make a multiple box plot of it and just see how it looks. What I'm looking at is with this Anova is to compare the means for all these different treatments. These are different treatments for each one of these samples. So let's do a box plot. Just like in linear regression, we did a scatter plot. First, it's good to do a box plot here and just to see if there's anything that stands out that says, probably don't want to do this. So we want to look at the weight, and we want it parameterized by the different kinds of, and I think the word is feed. Yeah, feed. Okay, this is going to give us multiple box plots. I'll pull these into the viewing window here, and you can see it's written some of the diets for the chickens down here at the bottom, and you can see the box plots for each one of these. There's a few outliers here in the last one, which I think was sunflower oil, but the rest of them look pretty good. And we can see that some of the means look very similar. The first one and the last one look fairly similar, and a lot of them look very dissimilar, such as the first and the second. So we're going to perform this analysis of the variables to see if indeed there is a difference. Recall that for this analysis we'll have 2 degrees of freedom. One will be for the number of different treatments, or the number of different treatments that are being given to these chickens. I think there's 6 of them, so that's n minus 1, which will give you 5. And then you have to look at the total number of variables. You can see that's 71 minus the number of treatments. So we're going to see that coming out here. Then there's several sums of squares. Then those sums of squares are divided by the degrees of freedom. Then that is made into a ratio, which is your F value, or your F test value. Okay, we can get all of that by just going, let's give it a name. I'll say that's what I did in the test. Okay, a chick. Okay, and the command in R is AOV. Very straightforward. And then you tell it the variable. We're looking at weight versus feed. Okay, let's print out what we get from this. And you can see the oh dear, what did I do? Okay, you get some of the parameters when you just type the name, but it's better to go with the summary just like it was with the least squares. That's where I got it. Okay. Now, what do we have here? We see the 2 degrees of freedom. One would be 5 because that's n minus 1, the other 71 minus 6, which would get the 65. Here are 2 degrees of freedom in the first column. Right. The sum of the squares is given here in the second column. The mean squares is the sum of the squares divided by the degrees of freedom. Then you divide these 2 mean squares by themselves and you come up with an F value. You're also given essentially a P value. And just with any P value, this is the probability that this value of F or something higher would have been achieved. And given that the null hypothesis is true. The null hypothesis is that all of the means are equal. So that there's no difference in all these treatments. As you can see, this p-value is very small, which means you would probably reject that null hypothesis. Instead of using the p-value, the other way would be to look at the critical F value. And you can find that by going QF. I'm not going to give it a name, we'll just print it out. Let's give it for 95% probability, and now we have to give 2 degrees of freedom, the 5 and the 65, and we want a positive value. Okay, and we see the critical value is about 2. The F value is 15, so that kind of verifies that the p-value of 5 times 10 to the minus 10th. Now the null value is rejected. We can now go back and look at the means 2 at a time to see which ones are very different, because of course we have quite a few here and there'll be a lot of comparisons. So that's done with the Tukey HSD command, and that's a highly statistical, honestly statistical difference, and that's a command we're going to use here, and it will just spit it out, so we'll just not give it a name. HSD, and we have to give it the analysis, which was a chick. Alright, and there it spits it out. You see how it looked at each of the feeds 2 at a time, calculates the difference, calculates the confidence interval for a 95%, based on 95% confidence level, and it also gives you a p-value at the end. As you can see, some of them are very different. Okay, these first 2 were very, very different. Some of them aren't very different. For example, the linseed and the horse bean. Here's another one that's not very different at all, soybean and linseed. Right. And that's basically it for your Anova analysis using R. And on the last page of the written tutorial, I just listed these commands as bare bones commands. Of course, judgment is what's really required here, but it's really nice to be able to get into something like R, and with a couple commands get out all of these calculations.